Hi, I'm Lisa Ann Hendricks, and today I'm going to be talking about deep compositional captioning, which is work done with my collaborators. The goal of compositional captioning is to build models which can generate sentences which compose different visual elements together in ways that haven't been seen together in training descriptions. So if we look at current models, current competitive models, they can do well on images like this. So for example, the Berkeley LRCN and the Microsoft Caption Bot are both able to describe this image. They're able to get the main object in the image as well as what the object is doing and, where the object is. However, in order to generate these sentences, these models need to have data which consists of pairs of images and sentences for training. So if we look at this data, we can note that the images are fairly similar to that test image I just showed you. And furthermore, any of these descriptions that are from the training set could be copied verbatim to describe that test image I just showed. So this made us ask, what happens when we give these models an image that can't just be described by a training description? So this is an example of one such image. This is an image of an anteater, and there just aren't anteaters in the paired image sentence data that we have. So consequently, the Berkeley LRCN and the Microsoft Caption Bot fail to describe this image. However, we can build an anteater classifier. This is something that we can do. And furthermore, if we look at these descriptions, they do get some things right, like there is something that is in the grass. So in order to describe this image with the data we have available to us, we need to be able to build a model which is compositional in the sense that it can combine the anteater with the grass in a cohesive statement. And that's exactly what our model does. We're able to generate sentences like, "A anteater is standing in the grass." So our model is called the Deep Compositional Captioner, or DCC, and it can compose descriptions about novel objects in context. Whereas existing methods rely on paired image sentence data to jointly model language and vision, we also look at unpaired image data, which is images with labels, as well as unpaired text data, which is just text annotations with no visual information. Our model DCC uses two key insights. The first insight is that if we're going to train with outside data sets, we need to make sure we're doing so effectively. And the way we do this is we have one part of our model which learns strong image features, and we train this only with unpaired image data. We have another part of our model that learns strong language features, and we train this only with unpaired text data. Finally, we combine information from images and language with a multimodal unit, which generates descriptions about an image. The second key insight is that if we can describe an image like giraffe, which appears in our paired image sentence data, we should also be able to describe words like impala. Likewise, if we can describe dresses, we should be able to describe tutus, and if we can describe cakes, we should be able to describe scones. We train our model in 3 stages. The first stage is training our lexical classifier. The lexical classifier is trained with unpaired image data, and the network we use is a VGG classifier with a multi-label loss. We use a multi-label loss because a single image can correspond to multiple different visual concepts. The final feature vector that we get is a vector with activations corresponding to scores for visual concepts in an image. For example, for this image of an impala on the left, we might have high activations for words like impala and sunny, and low activations for words like bus. The next stage of our model consists of training a language model. We train our language model with unpaired text data, and the network we use consists of an embedding layer and an LSTM unit. We're training this model to predict a word given previous words in a sentence, and the final feature vector that we get should be able to encode the previous words that were used in the sentence. Once we train our lexical classifier and our language model, we're able to extract strong image features and strong language features. We then transfer these weights into a caption model, and we introduce a multimodal unit which learns to combine image and language features in order to generate a sentence conditioned on an image. We train this multimodal unit with our paired image sentence data. So the multimodal unit we use is just an inner product layer, and the output is scores for every single word in our vocabulary. Because we use an inner product for our multimodal unit, our final scores are a linear combination of language features, denoted as FL, and image features, denoted as FI. So let's look at an example. Say we want to describe this giraffe, and so far we've generated the words brown. We expect our language feature to encode which kinds of words make sense to say after a brown. So we expect FLWL to be high for words like giraffe, horse, and couch. And we expect our image feature to encode the kinds of words that make sense given this image. So we expect it to be high for words like giraffe, trees, and standing, but low for words like couch. Alright, so what happens when we try and describe this image, which is not in our paired image sentence data? We still can't describe it because we've trained our multimodal unit with our paired image sentence data. In order to describe this word, which is not in our paired image sentence data, we introduce a transfer mechanism. In our transfer mechanism, the first thing we do is we find a word which is in our paired image sentence data that's similar to the word impala. And we do this using a distance measure in the word to vec space, and we find that giraffe is most similar to impala. Okay, so the score for the output word giraffe is equal to a linear combination of language and image features and a single column in the multimodal unit. In a similar way, the score for the word impala is equal to a linear combination of language and image features and another column in our multimodal unit, here denoted in green. In order to describe impalas the way we describe giraffes, we transfer weights from the giraffe vector to the impala vector. Next, we note that our image feature activation has specific activations which correspond to the word giraffe and to the word impala. If we have a high image feature activation for giraffe, we probably want to output the word giraffe in the sentence. And likewise, if we have a high image feature vector or a high image feature activation for the word impala, we probably want to output the word impala. So what we do is we transfer the weight which links the giraffe image feature activation to the giraffe output word to the weight which links the impala image feature vector to the impala output word. Next, if we have a giraffe in our image, it probably shouldn't influence how much whether we're saying impala or not, so we zero out these weights. Once we've implemented our transfer method, we can now evaluate our method because now we're able to describe sentences, or able to describe images which include objects which are not in our paired image sentence data. For evaluation, we use the MS COCO dataset, which is a dataset which consists of pairs of images and sentences. In order to get unpaired image data, we can still use the MS COCO images, and we can just take labels by mining the annotations. We can get unpaired text data by just looking at the annotations without the images. However, in order to evaluate our model, we need to have some words which don't occur in our paired image sentence data. So to do this, we take out sentences which include one of 8 objects in the MS COCO dataset, and we call this our held out dataset. All right, so to evaluate our results, we look at 2 baselines. The first baseline is LRCN, trained on our held out dataset, and the second baseline is DCC without transfer. We're also going to look at 2 metrics. The first thing we want to see is whether or not we're able to generate sentences which talk about objects which aren't in our paired image sentence data at all. And to measure this, we're going to use what we call efficacy, and we're going to use an F1 metric. And for those of you who are familiar with the F1 metric, what we are going to consider a true positive is a sentence which talks about an object which is not in the paired image sentence data correctly. Additionally, it doesn't do us any good if we can talk about these new objects, but we're not doing it in a fluent way. So we also look at the sentence quality, and we use Meteor to measure this. Alright, so looking at the F1 score, both LRCN and DCC are incapable about talking about words which are not in the paired image sentence data, so we have an F1 score of 0. Our model is able to get an F1 score of 40, which means it's able to talk about words which aren't in the paired image sentence data. Furthermore, when we look at the sentence quality, DCC improves upon LRCN and the DCC model before transfer. Next, so all of the models in the previous stage got to see MS COCO data for the lexical classifier, the language model, and then also the caption model. And this probably doesn't reflect a real-world scenario where we might not have unpaired image data and unpaired text data which come from the same domain as our paired image sentence data. So the thing that we do next is we evaluate what happens when we use out-of-domain data to train our lexical classifier in our language model. So if we use out-of-domain data to train our lexical classifier, we see our Meteor and F1 score go down a little bit, but not by too much. If we then use out-of-domain text data, we see that our Meteor score and F1 score stay about the same. So we're able to generate sentences with out-of-domain data. Alright, so here are some examples of sentences generated on our MS COCO held out dataset. So the word in bold is a word that is not in our, that was held out from the MS COCO dataset. And as you can see in this top image, we describe, before transfer, we say a green and white street sign on a city street, which misses the key object. Once we apply our transfer method, we see a sentence like a green and white bus parked on the side of the street. So we're able to talk about the main object, which is the bus, and we're able to talk about it correctly in its context. Alright, so the thing that I think is exciting about DCC is now we can talk about images that we couldn't talk about before because we're able to talk about objects that aren't in description data sets. So here I have 2 images from ImageNet and they have a gecko in them, and either the Berkeley LRCN or the Microsoft Caption Bot can talk about the gecko because they just haven't seen images of geckos before. However, DCC is able to talk about the gecko, and I think more importantly, it's able to put the gecko in the correct context. So it's able to say a person is holding a gecko in their hand versus a gecko is standing on a branch of a tree. So we applied DCC to to hundreds of different images and objects in ImageNet, and we're able to describe over 300 of these objects, which are not in any description data sets. And we can describe words like tutu and candelabra, and we can also describe fine-grained words like baobab. Of course, there are some failures. One failure case that we frequently see is the repetition of a word in the sentence. So, for example, a woman is riding a unicycle on a unicycle. And another error we see is incorrect grammar, like a group of people standing around a fox hunting on a field. Another place where I think DCC is exciting is when is in video description, where we have even less paired data than in image description. So we tried this on video description and we see the same trends. You can see some examples on the right and check out our webpage for more examples. Finally, since first proposing this model, my colleague Shubha has led the effort to make a model which is both end-to-end and can describe more ImageNet words than DCC. You can check out this archive. It came out yesterday, so if you're interested in this, I encourage you to look at it. Finally, we think that this idea can be relevant and useful in other language and vision tasks, like the referring expression models you will see in the next talk and in my colleague Rongheng's talk on Thursday morning. In conclusion, we have proposed a compositional captioning model, which is able to generate descriptions which combine visual elements which have not been seen together in training descriptions. Thank you very much.